So, since there were questions last time about philosophy and whatnot, I thought it's worth at least spending a little bit of time quickly reviewing at least um, a bit of the philosophy. Since when it comes to model building, if there isn't a reason to do it, you shouldn't be doing it, right? The philosophy is important. Why you're doing it is important, right? It's not like an experiment where you're just like, I want to measure this better, and its motivation is I want to measure something better, right? That's a good motivation for an experimentalist. For a theorist, writing a model just because you can is a terrible reason. And so it is worth talking about philosophy just very quickly. I'm going to give a quick top-down point of view. At least it's not exactly what I was saying before, but I think at least I can make it very, very explicit. So the question is, what do we want in a theory? Or maybe more accurately, what do I want? And I hope everyone has at least maybe not exactly, but a similar thing. And what at least I personally want is something actually rather ill-defined. I have some theory which has some inputs, let's say like its couplings, whatever. And I want an order 1 fraction here to be SM-like, whatever that means, and whatever the axes mean. Right? I want the standard model to be a generic output of my theory, or the standard model to look very generic. And I can sort of make this very explicit when it comes to QCD, or in particular the proton mass, which is if you just said, like Dirac did, the theory of the world is m proton psi bar psi for the proton, you might just say my input is the proton mass, could be 0, could be the Planck scale, and nature chose something that's so close to 0, that's 10 to the minus 18 close to 0. That's not at all a generic point in this parameter space. Looks like something weird is going on, and he did not like it. And what happened was, actually due to dimensional transmutation, the input parameter is the QCD coupling. Alpha S goes from 0 to whatever 4 pi, 1, however you feel like putting it. And then because m proton is m Planck, e to the minus 1 over alpha, or maybe not 1, but some number over alpha. Everywhere in here has m proton much less than m Planck, which is the goal of saying, yes, the proton mass is much lighter. And this is something like whatever, depends on normalizations, order 10-ish percent, whatever. And it looks a lot less crazy than this guy. So all nice and good. Let's then apply this to the Higgs mass, since that's really what we started to talk about now. Do the exact same thing. Draw a line, minus m Planck squared, m Planck squared. And it turns out that the Higgs mass, m Higgs squared, is much, much less than m Planck. Let's take absolute value. So it's a very, very tiny little point here where you have the Higgs mass being much, much less than the Planck scale. And the question is, why? Is there some nice elegant mechanism just like the proton mass, which sets this small? And so what we want, or at least what I want, is a theory that explains this, where over some large region over here is SM-like, SM-like being m Higgs squared is much less than m Planck squared. Some inputs, whatever. And people, very smart people, have started to say, okay, let's write a theory that has this property. And they did, and it's called SUSY. However, what SUSY does is draw the same thing. And let's say this is SUSY, everything SM-like is here. And then we put in experiment. And it turns out that just experimentally, everything here is excluded except for a tiny little point here, not excluded. Let's say this is SUSY. And we can ask, okay, does this mean we're about to discover SUSY? Does this mean, right, there's a small region of parameter space which has not been excluded yet. Is this a bad thing? And it is not necessarily a bad thing, right? Let's say we go back 20 years. Here's the Higgs mass from 0 to m Planck. And there was a lot of excluded parameter space from maybe up to like one, whatever, I'm not going to be completely accurate, 100 GeV. Let's say there was some 200 GeV. At some point in life, something like this was true. This is a tiny region of parameter space left out of the entire thing for the standard model. And this was not a bad thing. It just meant we were about to discover the Higgs, right? A tiny thing not being excluded is not a bad thing. And so we ask what happens there. And we will discover that actually we have more standards than what I just wrote. Namely, you look there, you can calculate the Higgs mass, m Higgs squared, and you discover it's something like 10, there are contributions like this. There's another one that has 10 to the 8 GeV squared, and this comes out to be 100 GeV squared. And you look at this and be like, well, this is weird. It's just like I have two contributions that are canceling to within a huge order of magnitude. This doesn't quite look right. And the way I formalized this not looking right is the fact that you can either just say I don't like cancellations, and so this is a bad situation to be in, or I can just say my own thing is I really like dimensional analysis since it's what got me into physics. And dimensional analysis fails. And now, whatever, this fails. And so for me, I basically then discovered that I have an additional criteria, which is most of physics obeys dimensional analysis, except for in weird points in parameter space. So this is dimensional analysis, okay. And then here's SM, okay. And I kind of want this region to be large, or this is SM, okay, SM-like. Okay, and so I was saying I want this thing to be large. And in the end, you could just say this is the end. This is really, I've stated my criteria. Just write a theory where I can show that the Higgs mass being its 100 GeV thing is a large fraction of parameter space. It's very standard model-like. Nothing crazy like this happens. End of story. That could just be the end. There's just one additional thing, which is you start building models to try to look for this, and you discover everything is looking like that. You cannot find a model. And what is the reason for this? The reason is actually very easy to say if we talk about the cosmological constant. So let's say we do the same thing for the cosmological constant, where we say, I want a theory where dimensional analysis is okay, and it's very standard model-like. And you can say, what can I say about this large region of parameter space? And because dimensional analysis is okay, I say my estimate for the CC must be milli-eV to the fourth because, well, or very small. All that really matters is this is a number much smaller than m Higgs to the fourth, m Planck to the fourth, just, it's a very small number. And I say dimensional analysis, because this has nothing other than units of energy, says the scale milli-eV is special somehow or another. And this is at great odds with experiment, where we've discovered nothing special, at least when it comes to the CC. There's plenty of other stuff, but when it comes to the CC, nothing special or nothing BSM with less than a TeV. And so the reason why it's so hard to construct a solution to the CC is because milli-eV is much, much less than the length scales we've looked at and energies we've studied. And so this is why, if you look at the CC, basically this is all excluded in any model that we know of, right? It's really hard to come up with a model that satisfies all of our personal criteria from the model. And yeah, and so, for example, you can make this extremely explicit for supersymmetry, where in supersymmetry, as a way of solving the cosmological constant says milli-eV is special. In SUSY as a solution, SUSY plus U1R as a solution, milli-eV equals scale of SUSY breaking rather. So at energies below it, SUSY looks badly broken. At energies above it, SUSY looks very good. And this means, for example, we should see the selectron at very low energy mass differences. We should see, let's say, the superpartner of the photon with a mass of milli-eV. But I have seen nothing below a TeV. And this new stuff I'm introducing has electric charge, it has color, it has all this crap. And so it's really easy to see, right? This scale C is the scale of SUSY breaking, and it's way too easy to see. Right? And so this is just making explicit the statement that once you make the milli-eV scale as special, the fact that we've explored up to a TeV means that it's really hard not to have a model that's already been excluded. And so let's repeat this argument for the Higgs, and you'll discover it's actually a lot better for the Higgs than it is for the CC, because that's whatever. Milli-eV to TeV is 1, 2, 3, 12, 15 orders of magnitude, right? That's, you're not going to get by being like careful with order 1 numbers or anything. You don't get 15 orders of magnitude out of nowhere. But for the Higgs, we're going to do the same thing. Same here. And we can ask, for the Higgs, what does dimensional analysis tell us? What is the scale that you estimate the scale that has to be special? The scale that has to be special, scale from dimensional analysis, is things such as like the M Higgs over the Yukawa, which ends up to being 100 GeV. Let's say whatever, let's write a number, so it's a 10 TeV. Okay. And now, though, you'll notice we've explored up to TeV, let's say. So if order 1 numbers work in our favor, and that the scale is 10 TeV, not 1 TeV, we don't actually have a problem, right? So if order 1 implies something closer to 10 TeV, then we're good to go. Then it's easy to be unobserved. Easy being a relative statement, because it's not like we have no probes of 10 TeV, right? Flavor physics is quite strong. We do have probes of 10 TeV. It's just much easier to escape experimental notice. 2, when we say we've been up to TeV, that's not entirely true. For colored particles, we've been up to TeV. Electrically charged particles, 300 GeV, and it's perfectly fine, right? Like electroweak charged particles are a lot harder to see. So what happens? What is at my scale is important. If it's easy to see, then it's going to be excluded. But even if it's at 100 GeV, if it's harder to see, and harder to see is not that much harder, you could just escape experimental notice. And then the final thing is, can you evade requirement of dimensional analysis? So the other way is to try to neglect, or not neglect, but reject one of the starting points. And so the statement at this point is, it's actually quite clear. Either you try to make sure order 1 numbers are in your favor, make sure what's harder to see any one of these works, right? By itself, could be very easy to see. If you get order 1 in your favor, great. If it's hard to see, great, it could be very low. Or if I just try to evade my constraints, and you're also good to go. And so this is basically what we're trying to do. Address one of these 3 points in different models. And the perhaps sociological point is that every model that was older than 10 years, so if you're older than 10 years, they're greater than 10 years or so, greater sim, you fail basically the top 2. Order 1 numbers basically never go in your favor, and at the scale turns out to be something very, very visible. Right. So the statement is simply that for the older models, they fail on these fronts. And so people are just trying to find new models that do not fail. And it's not impossible, right? Order 1 numbers can sometimes give you a factor of 10. Great, you're good to go. It's just they haven't found a model that did it yet. And there is likely one. Same thing here. What appears might be colored partners, which are very easy to see, or they might be something else. Like what appears might be something else, and then it'd be much harder to see. And yeah, and there are also issues, let's say, like if you try to really go down anthropics or the historical route of trying to evade the use of dimensional analysis. Okay, so this is roughly speaking, not exactly the way I phrased it before, but at least one very explicit way of saying what the philosophy behind all these problems are. Of course, very personal, but of course, a lot of this is a personal thing of whether or not you think cancellations are okay, whether or not you think dimensional analysis should always hold, et cetera, et cetera, et cetera. Right? I didn't write all the personal biases, like reductionism is a great way of wanting requirement on a model. I just sort of gave you a way to, at least using my personal biases, to get to where we are. All right, any questions before we go back to actually talking about models? Okay, so at least it's hopefully very explicit about assumptions, blah, blah, blah. Okay, so where were we? We were going down the model of a historical model, which was how might you evade the requirements of dimensional analysis. Might our universe just be like showing up in an experimentalist's lab where they decided they liked fine-tuned things, and so they by hand fine-tuned some stuff. And so again, the idea was, let's see, do I want to draw a picture? Yeah, I'll just draw the picture. You have a model where wiggles start and then get larger and larger. And here's a scalar, here's its potential. And you choose things in just the right way, such that at this point, m Higgs is about 100 GeV. So you'll notice at this stage, in some sense, we are giving up on the one of the things I said before of saying order 1 fraction of the parameter space should have something standard model-like. At this point, we just settled with some way of not being excluded, right? We've at some point lowered our standards of not being excluded, and then we'll hopefully try to make sure that it's sort of more beautiful in the sense of that. And the idea was like, if you live anywhere along here, then you could roll your way down to here. And if you start off anywhere over here, well, you're unlucky. And so maybe in some sense, maybe there's a 50-50 chance that you end up in the right with a small Higgs mass. So this is what they want the history of the universe is you just roll down here, end up here, and my history of the universe has a finite age, so I choose not to tunnel yet. Okay, so very quickly, the Lagrangian that we wrote that does this involves, let's call the UV cutoff of this theory m squared plus, I'm neglecting all order 1 numbers. Okay, well, let's write the Higgs mass first. H squared plus lambda h to the fourth. And so you see that by construction, the Higgs mass depends on phi. It can be positive or negative depending on the sign of that term. And then we wrote another term. This is allowed by dimensional analysis, so we write it down. Being sloppy, of course, with order 1 numbers. So this is the linear term we see here. And finally, the term responsible for the wiggles, phi over f gg tilde, which I said, roughly speaking, generates a term which is lambda QCD cubed, a Yukawa coupling of roughly the up quark or the down quark. It's a bit times the VEV of the Higgs times cosine phi over f. Maybe plus theta if you feel like it, things like that. There's a phase. So the wiggles get larger when the Higgs VEV is negative. So over here, Higgs VEV is large by some definition of large. Here, the Higgs VEV is either small, Higgs VEV is small or 0. For example, positive Higgs mass. Okay, and by just choosing, right, kappa is a parameter in my theory. At this stage, I will choose it to be something. It is technically natural to choose it to be small, and that's what we will do. We want the first derivative to be non-zero, or first derivative to be 0, so that you can have a minimum. And so first derivative v prime kappa m squared plus y. Let's just call this mu, which is of phi lambda QCD over f times an order 1 number, since the sine or in cosines turn into an order 1 number, equals 0. Order 1 can be negative too, so if you want to balance the two against each other. And you can see I get the right value of the VEV if I choose this, if kappa m squared f is of order the observed value of 100 MeV to the fourth here, then minima appear just when the Higgs VEV gets to its right value. So this is the idea behind it. And at this stage, we'd say these people, the relaxion people, have set off to do what they claimed. And it's just an issue of dotting all the I's, crossing all the T's, looking for anything that might strike you as weird and things like that. So as an example, let's sort of list some of the things at least they thought they had to be concerned about. And then I'll start pointing out either problems or you can call them opportunities, depending on if you choose to fix them or not. Okay, so first thing is their choice of friction, right? Because you'll notice if I'm rolling down there, I pick up kinetic energy and I'll just go flying past all the wiggles unless there's some friction term to lose energy. So their friction comes from doing all of this during inflation. And this is when I regret choosing H to be both Hubble and the Higgs. FML. Okay. This means the equation of motion of phi involves a term 3h. We can balance it against, so let's say I'm rolling over there. I can balance it against the linear term, which is kappa m squared. And so, for example, I'll have to have the constraint phi dot squared. The kinetic energy is less than the scale of those humps, right? So that I don't have enough kinetic energy to roll over them. Roughly speaking, this will just be less than 100 MeV the fourth. Exactly at the first place, there's some issues with it being a little flat, but the wiggles have size 100 MeV to the fourth, when we're stopping. And so my kinetic energy should be small. What else? Okay. What other things did they write? So because they were using friction coming from inflation, they just wanted Hubble not to change during this entire process. So you'll notice as phi changes, so phi changes from the Higgs mass being large positive to 0. So it has to go through an amount m squared over kappa so that you can actually take yourself from a positive 1 to a negative 1, right? So it changes by a large amount. And in this process, changes vacuum energy by how much? It changes it by the linear term m to the fourth. And I want this to be less than or equal to h squared m Planck squared, which is the energy density in the inflaton. So this is the inflaton energy density. So I don't want to have anything to do with inflation. So I make sure all energies involved are very small compared to the inflaton. What else? They wanted to avoid inflation, or rather they wanted to avoid eternal inflation. So in particular, they wanted to say the average delta phi in a Hubble time, or rather 1 over Hubble time, is phi dot times delta t. So that's kappa m squared over Hubble squared. And I guess we're not really, maybe Maldacena told you, but sort of fluctuations in phi in a Hubble time are of order Hubble. And so you need the classical motion to dominate over any quantum stuff if you want inflation to end, or in particular, this guy not to drive eternal inflation. So they wanted this to be greater than Hubble. So this is an additional constraint. And let's see, what else? We had this constraint. And they had one more thing. What was it? Oh no, I think that was it. Okay, so these were the constraints they were looking at. And it results in quite a few odd things. Not odd in the sense of dimensional analysis, but odd from other points of view. And depends on your personal biases about a lot of stuff. So do I want to just derive it with those three? I guess I can. Let's remind myself real quick. So experiment implies F is greater than 10 to the 9 GeV. So this is just looking for this particular coupling. They're just experimental constraints on it. Let's say supernova. Supernova are about this. Combined with this guy here, you can say this means kappa m squared. F is greater than something. So this is less than or equal to 10 to the minus 13 GeV squared. We can now impose, so this comes from that, we can now impose that guy up top. Kappa m squared is greater than Hubble cubed. So this implies Hubble is less than this thing to the 1/3, roughly 10 to the minus 4 GeV. So you're going to need a very low scale of inflation to pull any of this stuff off. You can then impose the last guy here. Hubble is less than 10 to the minus 4, and Planck is 10 to the 18. So this is m is less than 10 to the 7 GeV. So you can't solve the entire hierarchy problem. You have a UV cutoff that's at 10 to the 7 GeV. And I guess plug this into here. What do you get? Kappa 7 squared 14. Kappa is less sim. This is cubed. 14, 10 to the minus 27 GeV. Which we'll get, the final thing is we're going to change, just estimate the number of Hubble time it takes for a phi to change. So we need how many number of e-folds of inflation. We need delta phi is number of e-folds of inflation times 1 over Hubble phi dot, the amount of time it changes. So this is n kappa m squared over Hubble. We can now, how do we want to turn this? Great, this should be larger than the total change, m squared over k. So we can combine this to get n is larger than, maybe I shouldn't have erased this one. N greater sim Hubble squared over kappa squared. We can put in our value of Hubble, 10 to the minus 4, 10 to the minus 8 GeV squared. Kappa is what, 10 to the minus 27, so 10 to the minus 54 GeV squared. You get what, 48, or no, 46? 46. All right. So great. So this is sort of the first model of people wrote of the relaxion. It has some requirements: large number of e-folds, very small Hubble. You can get to a UV cutoff of about 10 to the 7 GeV. You require some really small couplings that you will eventually have to explain. Yeah. Okay. So great. So at this stage, you have gotten around experimental constraints, and you should start trying to look for problems. You should start trying to poke holes, or put another way, opportunities for improving the model, if you so choose. Okay, so problems / opportunities. So people, after this original paper came out over, I don't know, like 8, 9, 10 years ago, probably about 8, maybe, maybe closer to 10. Years ago, people have spent a fair bit of time trying to fix some of the problems and sort of doing other things with it. So what have been some of the things? One, let's go in no particular order. If you talk to, or if you think about inflation, it turns out to be pretty hard to get 10 to the 46 e-foldings of inflation and Hubble this small. And so inflation is hard. So what have people done? Well, like I said, right, these are problems and opportunities. People try to solve the problem, which is, why does this have anything to do with inflation? Because I needed friction from Hubble friction. So you can solve this. Solve with new source of friction. And that's what people have done. So you can make the inflation aspect of this story and just go away, right? You could just complain and be like, 10 to the 46 is an insane number. I'm not going to think about things. Or you can find a new source of friction. For example, If this particle phi can decay, then its energy density disappears into other stuff, and you can just have a new source of friction. So this is one of the things people have done to try to solve the problem, this particular one. Other issues. Okay. Two, you'll notice delta phi is much larger than F. We can even quantify this. F, we had said, was 10 to the 9 GeV. Delta phi is m squared over kappa, m squared 10 to the 14 over kappa, 14 plus 27, 41. So this difference is 32, yes. It travels a distance 10 to the 32 more than F, which is also much larger than m Planck, and et cetera, et cetera. And so again, another thing you'll see, in fact, this is, if you had talked to any, whatchamacallit, string theorist or whatever, when this paper came out, they complained inflation is hard, so you should not care about the model. Delta phi is large, so again, you should not care about the model. Turned out everything like this has been solved. You can just introduce new sources of friction. You can get around this by a nice model that David Kaplan and Riccardo Rotazzi did called the clock working, where what they basically did was, I'm just going to tell you, you can look up the model yourself if you're so inclined, but what they did was they just said this ratio here, delta phi over F, can be made to be 3 to some number, n. And n is just like some number of particles. And so, in fact, you could turn the 3 to like other higher numbers if you so felt like it. They just gave the example of 3. And so you could, means to explain 10 to the 40, all you needed to do was what, 3 to the whatever, roughly about 100. And so they took a 10 to the 41 number, turned it to 100. If you decide to put this to be 10, you can get 40, et cetera, et cetera. You can sort of play with it however you like. But either way, you can take something that's exponentially bad, take the log of it, and get something that's only logarithmically bad. So this is basically the spirit of how you solve a lot of problems in particle physics. You just take the log of the problem. And people, well, combined with a bunch of marketing, this became almost as popular as the axion itself, or sorry, the relaxion itself. Okay, so these were sort of more experimental sides. You can also ask theoretical problems, right? There are conceptual issues of trying to implement any historical model. So these are ones that you can try to solve. Do I care about any of these? Probably not. But okay. Great. So what are some of the conceptual problems that you have to try to solve? Conceptual, these are generally tied to all historical approaches, but not all of them. There is the why now problem. So in particular, what they said was you roll, you stop at a bump, and that's great. That's where everything is. But why do you not tunnel? You have eternal inflation in the late time universe. And then if your age is infinite, inflation, then why do you exist at near the beginning of the universe rather than near some whatever, some very far future? So there's why now of why was any of this was important? Why did you not tunnel and other stuff happen? And let's see, there's some additional things such as like making this cosmological constant much harder and things like that, which are tied to this. Okay, so people have tried to solve some of these issues. Notice eternal inflation, eternal inflation is tied to the CC problem, so that's going to be very hard to solve. But the why now problem, you can, and people did try to solve by saying things like, what if this is tied to reheating? So what if when you arrive at here is when reheating happens, right? This triggers reheating. In fact, this is sort of tied to other sources of friction, because if you're rolling down the hill here and then suddenly all your kinetic energy turns into friction, which means you populate a thermal bath, this means when you reach right here, you get as hot as you'll ever get in the universe. And so you can try to solve some of these conceptual problems as well by doing other things like tying it to reheating. And then as for why reheating is tied to why now, you have to appeal a little bit to anthropics. Okay, so this is sort of a case study of going through a model. You try to solve you have a great idea, which is, I know other problems are solved in a historical manner. So what if our problem is solved, the Higgs is solved in the exact same way? And then you start trying to get a model that works. You write a model that is not experimentally ruled out, does what you claim to do, and then you try to look through some of the issues and fix them, and both on the more perhaps experimental and easier to sort of work around, and sort of the more conceptual issues. So this was basically just supposed to be case study of how you can try to go about this thing, which is historical solutions. Okay. Any questions on the relaxion or? All right. So I'd said, at least when I try to approach a problem, personally, I think I'm a generic physicist, generic problem, a generic solution. So I look for all the other generic solutions that have been around before. And so let's talk about other generic solutions, not historical ones. I gave that example. Let's look at relaxation solutions. Okay, so let's try to argue that relaxation solutions are not only a great solution to a problem, but one we have seen all the time in physics. So an example I particularly like about this, when it comes to this, is I give you a carbon dioxide atom as CO2. And I go to an experimentalist and say, measure the electric dipole moment, measure its EDM, and they come back and tell me this thing is equal to 0, exactly. There is absolutely 0 electric dipole moment. And I go, well, that's quite confusing. Let me here grab a carbon dioxide molecule. I have my hands over here. I'm squeezing a carbon dioxide molecule, holding it, and be like, I can calculate the EDM here. This has a small plus charge. This is a minus charge on the oxygens. Look at this. The dipole moment is sum of Q times distance, and it's not equal to 0, right? And you'd be like, what are you doing, you crazy experimentalist? Here, let me grab one, show it to you that it's non-zero. Okay, what would the experimentalists say? And they would say, you're an idiotic theorist. You can't grab a carbon dioxide molecule. What you do is you just have a gas of it, hold it roughly in place very, very weakly. Your tweezers are not very strong at all. And what happens is the carbon dioxide atom relaxes to its equilibrium state, right? The minus charges there repel each other. It emits a little bit of radiation, and it ends up here. You started off here, it goes here after whatever, 1 millisecond, however long it takes to sort of radiate off some energy. And you say, look at this. It has nice charge time dipole from here plus dipole from here, implies the dipole moment is 0. Great. Great solution. And this is actually the solution to the problem. What happens is if you start off with a random carbon dioxide, maybe it's thermally excited, who knows what happens. It just sits there, it relaxes itself, and it becomes, the dipole problem disappears, right? I have a very small number. It's explained because, sure, it might be non-zero. I just wait a bit of time. This angle here, right, the dipole moment is something like some charges times the distance. Is this sine or cosine? This is probably something like cosine theta over 2 or something like that. My math on the board is terrible. But you wait a little bit of time. This angle changes as a function of time, and it becomes 0. And so this is the relaxation solution. And you can do, this happens all the time whenever you do stuff in classical mechanics, right? Because in classical mechanics, stuff is oscillating all over the place. Things that you thought were a constant theta are not actually a constant. There's some degree of freedom that radiates and does its stuff, right? So the idea then behind this new class, this relaxation solutions, let's just summarize quickly, is I have a question. Why is something small? Why is XXX small or 0, right? Because actually it takes, technically speaking, it takes infinitely, it's an exponential decay. It'll take an infinite amount of time to lose all your energy and whatnot. Well, at least classically, it'll take an infinite amount of time to really get it exactly to 0. It's just you eventually just get it small enough. So the idea behind relaxation is why is something small? And the answer is, well, XXX is a function of something else. Let's call it theta. Theta can change. And I wait until XXX of some value, let's call it 2.3, where it relaxes to equals 0, because the minimum energy has XXX equals 0. This is what it takes to do a relaxation solution, is that the thing where whatever it is, electric dipole minute, whatever, equals 0, is a minimum energy configuration. And if it's allowed to change, it can go to its minimum energy configuration, right? So there are 2 steps to any relaxation solution. Okay, basically, so the 2 steps of any relaxation solution. 1, make whatever your is a function of something that can change. That changes. The second step, hope or arrange XXX of theta equals 0 is minimum energy. Okay, so in some sense, all relaxation ideas are very simple. It's basically take any problem, make it look like this carbon dioxide type example, or there's a million and other classical examples. Things like methane and whatnot have other situations like that. But Any questions on basically their goal? All right. If not, it'll take a long time to go into introducing all this and give an example that does this for the Higgs mass. So let's have a quick break, get ourselves some coffee, and then we'll reconvene afterwards. Okay, everyone. I guess we've roughly gathered. So let's repeat what our goal is here for relaxation models. So what we're going to do, we want to relax the Higgs mass to 0 because the question is, why is the Higgs mass so small? If we can get it to 0, we can always make things larger than 0, but getting it small is the issue. And so first, we want to say, make Higgs mass a function of something. Function of something. And then we're going to say, or try to arrange the minimum to be arrange minimum at m Higgs as close to 0 as possible. Okay, so great. So how are you going to go about doing this? Let's start with just the second part. All right, so let's start with what is the vacuum energy? Where is it? What is the vacuum energy of the theory as a function of the Higgs mass, right? Because we want this to be minimized at m Higgs equals 0. So our first step is like, what about the standard model, right? What is mv as a function of m Higgs squared in this case? So we start off with v equals 1/2. Okay, I'm going to be sloppy with order 1 numbers again, like I said before. Okay, so sloppy with order 1 numbers. We say if the Higgs mass is positive, Higgs squared greater than 0, this implies the VEV of H equals 0, which implies V equals 0, right? So if we plot, let's plot it over here. Okay. So let's plot V as a function. Oh, I guess I could even put positive and negative here. M Higgs squared. And when M Higgs is positive, this is the tree level. You're not going to see it. Okay, you're not going to see green very easily either. Let's try red. Okay, well, let's do plus a constant. Add in the CC that we're not trying to solve. Great. So here we go. It's flat. That's all that really matters. Okay, great. What about if it's negative? If m Higgs squared less than 0, then we minimize this, right? Take the first derivative equals 0. The Higgs VEV is absolute value of m Higgs squared, square rooted, divided by, I think it's square root of the quartic. And then again, order 1 numbers, blah, blah. Okay, great. Plug this in back there. What do we get? There's actually an important sign here that you have to notice. I'm being sloppy with signs, but it turns out to be negative m Higgs to the 4th over the quartic coupling. Okay, and I'm taking it to the 4th power, so I don't care if m Higgs squared is positive or negative. Okay, so this means that this is our picture of V of phi. So as a model builder, we're like, ooh, so close. We wanted m Higgs squared to be a minimum. Actually, it's a maximum in the standard model. So as a model builder here, we decide, oh, let's get around this. Let's turn a minimum into a maximum somehow, right? Because let's say I start off here. You might be like, oh, but this is a maximum, but this is a maximum, this is a maximum, this is a maximum too. And you can ask, okay, is there some way to actually make this a genuine maximum? And I'm going to just say, well, what if you tilt this a little bit, right? If you tilt it a little bit, then you can very easily see that you can make m Higgs near zero a minimum or a maximum, a genuine maximum. The smaller I tilt it, the more of a maximum it is. So in other words, I have a free handle here to put it zero, the maximum, as close to zero as I want by tilting as little as I want. So I have a lot of things going for me right now, right? I can get really close to zero, but not exactly zero. Great, that's exactly what we observe. In other words, when I drew this, I could even try to go to one loop order and hope that this picture, the tilts and other things are small. And it's easy to actually make m Higgs a function of something. That's what the relaxion and a bunch of, couple it to anything. And then as you change something else, the Higgs mass will change. The whole trick, the only difficulty, model building wise, of getting this idea to work is to make the Higgs mass to multiply by -1, okay? This -1, it's hard, but not insurmountable. It is possible to get this thing and just turn it upside down. All right, so let's just prove that it's possible by giving an example. Okay. And in fact, let's write what this function is, just since I might use it later. V of m Higgs squared equals, let's see, it's 0 if m Higgs is positive. So that's a theta function on m Higgs squared. Wait, theta functions are what? 1 when it's positive. I want this to be negative. So theta of minus m Higgs squared. Then there's a minus sign, m Higgs to the 4th over the quartic with some order, one number, that whatever. Okay, this is going to be our basic starting function. So I'm just going to call this whatever, BSM, let's say. So I can reuse this later. Okay, great. Let's put a minus sign on all this. Where did that use? Okay, so great. I'm gonna choose, well, I'm just gonna, how I got here was a complete accident. So let's just write the model and then just say, there might be other ways to get the minus sign. I'm just gonna write a model that does. So what am I going to do? I'm gonna start off with, for reasons that I'm not really gonna tell you, to say I have 4 Higgses, H1, H2, H3, H4. And I'm going to have a Z4 symmetry under which this goes to this, this goes to this, this goes to this, and this goes back. So 4 guys that are cyclically exchanged. Next, I'm going to say, whoops, do not push up. I'm going to have a scalar, phi. It's an angular scalar because, well, I don't know if it's a theorem or not, but most of the examples I know of, especially in classical mechanics, of relaxation solutions tend to involve angles. And so we're going to write an angular field here. This phi equals phi over f plus 2 pi. So we're going to write an angular field here. I don't know if it's, like I said, I don't know if it's a theorem, but just practical experience seems to indicate that relaxation solutions like angles. Okay, And under Z4, I'm going to say this is like spokes of a wheel. It goes a quarter of the way around. So phi f goes to phi over f plus 2 pi over 4. Okay, great. Any EFT we're going to do, we're also going to have to write spurions. We're going to say, how does phi couple to anything in the problem? So let's say how angular fields couple. What is the spurions? If you're going to do spurions with angular fields, what do spurions look like? So we're going to write a spurion. And then at the end, we'll write everything allowed by symmetries. My spurion is going to be, I rotate phi over f, an angle alpha, and kappa, I used kappa already. Well, I did it for the relaxion, so whatever. I'm going to say kappa goes to, let's say it's kappa squared. It's a dimension 2 guy, dimension 2. It goes to itself times e to the minus I alpha. So this guy has charge 1 under spurion, and this guy shifts. Okay, this is going to be a generic thing. Angles shift under rotations. Other guys get rotated, multiplied by phases. Okay, and now EFT. Write down everything allowed by symmetry, right? This is, you start off specifying the symmetries of your problem, your spurions, and then write everything allowed by symmetries. EFT, everything. Okay. Let's just write, okay, well, I'm going to, let's give a rule of thumb for angular guys, which is we want to write a Lagrangian that does not transform under Z4, does not transform under kappa, does not, or the spurion symmetry, nothing. So we're going to want to have k squared, which gets rotated by e to the minus I alpha, and we're going to multiply it by e to the I phi over f. Notice this thing invariant under my spurionic symmetry. So my Lagrangian is going to be a function of this. Notice though that this does transform under my Z4 symmetry, because my Z4 transforms phi, but does not transform kappa. So let's write, at this stage, write everything allowed by symmetries. Okay, let's, whoops. I guess I was using M for the UV cutoff before, so whatever, let's use it again. M squared H1 squared plus lambda H1 to the 4th. Now, let's make this theory Z4 invariant. If I apply Z4, it takes H1 to H2. So it's also going to be plus M squared H2 squared plus lambda H2 to the 4th. Apply it yet again. H3 lambda H3. And I should really have used board management better because now you can't see the top part. So, okay. All right, so first step, got something Z4 invariant. Still not the most general Lagrangian consistent with symmetries since I have, well, I guess I have kinetic terms that I'm not going to bother writing down. Plus kinetic. Great. So now let's start putting in these kappa squared e to the I phi. So what can we do? First, this has dimension 2. So we can couple it to here. We want to write, for now, dimension 4 or less. So this has kappa squared e to the I phi over f h1 squared. That's a complex number. I need a real number. So I'm going to be plus its Hermitian conjugate. Kappa star squared e to the minus I phi over f h1 squared. And this is the only thing I can write down coupling it to the Higgs, h1, right? I'm just going to pretend this is, for example, an SU2 doublet or something, so I can't write a term linear in h1. This is all you can write down. Now we're going to Z4 it. I only did it for one. Rinse and repeat for everything else. E to the I phi over f. Phi over f goes plus what? Pi over 2. This is e to the I pi over 2 is what? Well, whatever. It's going to be plus I pi over 2 h1 squared plus complex conjugate. Right? This goes to that under Z4 plus kappa squared e to the I phi over f. Another z, so that's e to the I pi. Oh, this is probably like i's and minus signs. This is 2, this is 3, plus cc. And then we do it for the fourth guy too. E to the 3I pi h4 plus cc. Okay, this is almost the final answer of everything we can write down. Let's note, you can write Higgs cross quartic, lambda cross quartic q, cq of h1 squared h2 squared plus dot dot dot. For simplicity, I'm going to set them to 0. None of the math actually changes. It's just I want to be able to do the math on the board. So can be there. I'll set be there, but I'm going to set it to 0 just so I can do math by hand. Otherwise, minimizing this thing will be a huge pain in the ass. Okay. So if you want this non-zero, go talk to a computer. Okay. And you might say, notice phi is always coupling to anything. Can't I write a mass term for phi? So let's try to do that. Whatever, it doesn't matter. People will remember this, hopefully. Okay. Great, so what if you tried to write a term kappa squared e to the I phi over f times m squared, right? I want to just write a mass term, add its complex conjugate. Oh, this is a cosine potential, right? It's a mass term. Plus, let's erase the z4. Let's make this z4 invariant. Plus m squared kappa squared e to the I phi over f e to the I pi over 2. Okay, you can see these guys are all the same. So this is actually z4, it's m squared k squared e to the I phi over f 1 plus e to the I pi over 2 plus e to the I pi plus e to the 3I pi over 2. Okay. Notice 1 plus I plus minus 1 plus minus I equals 0. There is no mass term you could write here. Okay, I am nothing if not determined as a model builder. If writing it like this doesn't work, let's write kappa to the 4th e to the I2 phi over f. Right? This is the other thing I have available to me before I have to go to higher dimensional operators. Let's do it again. 1 plus this thing plus 2i pi. So there's a 2i pi over 2 times 2 plus e to the I pi times 2 plus that guy. This is 1 minus 1, 1 minus 1. This is also equal to 0. So there is no way to write a mass term for this scalar at the renormalizable level. You're going to have to go to higher dimensional operators if you want to write a mass for this guy. So a neat thing, if there are ever any zeros in physics, there's a reason, okay? This, I brute forced it to show you that the mass is always 0. Let's find a very quick way to show that it's non-zero, or why it's 0. Let's just try to write a mass term. So the Z4 symmetry sends phi over f to phi over f plus 2 pi over 4. So cosine phi over f is not Z4 invariant, right? Cosine 2 phi over f is not Z4 invariant. Cosine 3 phi over f is not Z4 invariant. Only, oh, that's right. Only cosine 4, 1 second. You guys did not catch, did you guys? Cosine 4 phi over f is going to be Z4 invariant. Or sines or cosines, these are plus phases, right? I have complex numbers here. Like kappa is a complex number. Things are going to be phases. And so I'm going to need quite a few insertions here before I get anything non-zero, right? But you'll notice cosine phi, morally speaking, this is cosine phi over f to the 4th power, right? It's the 4th harmonic. Every cosine phi over f comes with a kappa squared. So this is going to be kappa squared, the 4th power. You can see if I want to just write this down in my Lagrangian, UV cutoff m to the 4th power here. Okay. Yeah. This? This, yeah. So what is with this? I have to write the Z4 guys. Kappa squared cosine phi over f plus 2 pi over 4 to the 4th plus dot, dot, dot. Because you'll notice this has a lot of this doesn't just have the 4th harmonic, it has other harmonics. And then you will find the only term that is phi dependent is kappa to the 8th over m squared cosine 4 phi over f, right? This is saying, pictorially, what am I doing? I have a wheel that I'm rotating from here to there, half a quarter of a degree. And if I want something that is just a function of phi, it has to be a function of 4 times this so that it goes back to itself, right? The only thing, yeah. So this is saying the spurion here has to be to high power. And so as an EFT person, my mass term is going to be quite small. This is just brute forcing it, trying to write something. You'll find it always doesn't work. The highest order, the first time you'll find something non-zero is this guy here. And plus a phase. I keep on forgetting the stupid phase. Okay. So this is, for example, you can say, well, I might as well, from this point of view, have called this guy, um, I'm not good at board management here. I might as well have called it, capital F equals little f over 4, and Z4 sends phi over capital F to phi over capital F plus 2 pi, right? If I multiply everything there by 4, I have this. Oh, so obviously this means I write everything as a function of cosine phi over capital F here, right? From the beginning, I know not to write fractional powers here, non-integer powers. So I might as well just done this to see that you always need the 4th power here. Okay. A bit long-winded, but the moral of the story, this thing we wrote, is everything consistent with symmetries? Okay. Great. Let's save ourselves a little bit of math when talking about this and write this in a slightly more compact form. What am I going to do? I'm going to write, let's say, look up there. Look at, let's say, this last term here, kappa squared plus its Hermitian conjugate. This is, that term in the Lagrangian is kappa, the magnitude of kappa squared, cosine phi over f plus a phase, theta kappa, times h1 squared. Could be sine, cosine, whatever. Okay. The next term, let me see, this is cosine plus 2 pi over 4. Cosine plus 2 pi over 4 is negative sine. Let's simplify ourselves. Negative sine phi over f plus theta k h2 squared. This is, okay. Well, hopefully this is going to do another plus 2 pi. This is going to be, let's write it here then. Magnitude of kappa squared. There's a minus sign, so sine goes to cosine. Cosine phi over f plus theta k, h3, minus or plus kappa squared sine phi over f plus the phase, h4. Okay. That simplifies it a little bit. It takes 2 terms, makes it to 1 for each of those lines. Let's simplify it just a little bit more. We're going to introduce a function mh squared of phi over f is going to be the mass of the Higgs squared. The mass plus kappa squared cosine phi over f plus theta kappa magnitude. Great. Okay. So what do I have? I have the standard model with, this is the first guy, phi over f, which is just m Higgs squared of phi times h squared plus lambda h to the 4th. And we have 4 copies of this. SM2 of phi over f plus 2 pi over, that's pi over 2, plus SM3 phi over f plus pi, SM4 phi over f plus 3 pi over 2. Okay, so you can now see why I sort of set the cross cortex to 0. So I can just say there are 3 copies, each with slightly different Higgs masses here. Otherwise, completely identical. Now, I've solved what this is, right? I called it VSM. It is, if this is negative, then it's m Higgs to the fourth over land quartic coupling. And if it's positive, it's 0. Okay. So great. Let's say, so what does that give us? This gives us the first term is there's a theta function of mh squared of phi over f. What was it? It was when it's negative mh squared phi over f fourth over quartic coupling. And now I'm just gonna, this is my v of phi over f, right? It's just four copies of this, all with slightly different phases here. Plus theta minus mh squared phi over f plus pi over 2. There's a minus mh to the fourth pi over f plus pi over 2 over the quartic coupling. And then there's the pi piece and the 3 pi over 2 piece. Okay. And now I just want to draw a picture. So v as a function of phi. Okay, let's choose a random point. Okay, I don't like theta functions. Let's just choose when everything is negative. Whatever. Choose when all the thetas are negative, or all the masses are negative. And so I can get rid of the theta function. Okay. Say all m Higgs squared less than 0. So the theta function is, there are no theta functions. What do I have? I have negative 1 over lambda times all 4 of these guys. There's the first Higgs mass, m squared plus kappa squared cosine. Okay, I'm going to save some math by just setting the phase to be 0. Just save some math. This thing squared plus m squared plus kappa squared plus pi over 2 is minus sine phi over f squared m squared minus kappa squared cosine phi over f squared. And then m squared plus sine phi over f kappa squared squared. What is this? This is m Higgs of the first guy to the fourth, m Higgs of the second guy, third guy, fourth guy. Okay. Let's just do the sum and see what is this equal to. So need to somehow get better board. Okay. So first term, there are m Higgs to the fourth, or m to the fourth, plus m to the fourth, plus m to the fourth, plus m to the fourth. So first term is just minus 4 times m to the fourth over quartic. Okay, no thetas or no phi over f's. Now we do, let's say, the cross quartic, or not cross quartic, cross term. This thing is squared. So we get minus m squared k squared. We get the cosine. We get minus the sine. We get minus cosine. And then we get plus sine. Cosine minus cosine, sine minus sine equal to 0. Let's do the same thing. Last term, next term, this plus that plus that plus that squared minus 1 over quartic coupling, kappa to the 4th. Last term squared is cosine squared. Next term is minus sine squared. So it's plus sine squared phi over f plus next term cosine squared or minus cosine quantity squared. And last term sine. Okay. Cosine squared plus sine squared equals 1 equals 1. Okay. So notice, took a bit of work. This is equal to a constant. Constant, yeah. Okay. So great. This is when all of the m Higgs squareds are negative, all 4 of them. What happens when one of them becomes positive? Well, our theta function flips sign. So let's say m1 squared becomes negative. So let's say m Higgs 1 squared is greater than 0. What I'm missing is that first term there, right? That first term is now no longer there because the theta function sets it to 0. So what am I going to do? I'm going to add and subtract that, right? This is now what we're going to do. This is V before V4 minus first piece, right? I'm going to add and subtract that piece. This is equal to a constant. The first piece is just the Higgs potential, right? This is the minus m to the 4th Higgs over quartic. Minus, minus, this is constant plus mh to the 4th over quartic. Notice the plus sign, not minus sign. We have successfully flipped the sign of everything. In other words, as the Higgs mass goes up, like that. And what is right here, the transition? mh1 squared equals 0. Okay. We have essentially set out what we wanted to do before. We have a potential whose minimum is at the Higgs mass equal to 0. Okay. Now, turns out we have 4 Higgses. And so if you continue the story, you're going to have 4 bumps here. This is when mh1 squared is greater than 0, mh2 squared is greater than 0, mh3 squared greater than 0, and I guess I need a 4th guy here. Bump, and then it becomes periodic. Identify the left side part of the board with the right side part of the board. And at this level, I'm still only working at tree level. I can set this as close to 0 as I want, right? Because at this point, all I have to do to get it as close to 0 as I want is to say there is a new spurion, epsilon to the fourth, cosine 4 phi over f. And just say I'm just adding this to my Lagrangian and choose this as small as I want so that I get pushed as close as I want to that point. This is, I have to choose a very specific phase, get lucky that it's pushing you towards here rather than away. But plus phase, theta. So at tree level, this guy lets me do as small as the Higgs mass as I want, from the Planck scale all the way down to 100 GeV, if I just choose this guy correctly. Okay. Yes. Yes. Excellent. So the question is, I have one spurion, so this is my spurion, which is kappa squared, not cosine, kappa squared goes to kappa squared e to the minus I alpha, phi over f goes to phi over f plus alpha. Okay, and now I want to write a mass term that involves this thing to the fourth power, or the fourth harmonic, right? But you'll notice, what do I want to say? If I just write cosine phi over f, actually, let's just write it in exponential. Well, yeah, let's just write it cosine 4 phi over f with just whatever number I want, m to the fourth. This does not respect my spurionic symmetry. So this does not respect all the symmetries of the problem. Now, so this is not invariant under this symmetry, because this is saying when kappa goes to 0, this has a shift symmetry. It should be massless. So its mass has to be proportional to this to some power. Let's just figure out what power, right? This is e to the I 4 phi over f plus its Hermitian conjugate. So we can see, well, if I write kappa squared e to the I phi over f to the fourth power, now I have the right term. But now I need dimensional analysis over m to the UV cutoff. Let's even try to put it at the Planck scale to the fourth power. And so you can see, depending on what value this mass could be very, very small, right? And so, in fact, yeah. And so you'll notice, in fact, let's say I want to make this as small as I want, right? Like, is there some way to just by hand dial this down to as small as I want? Well, why is this a 4? This is a 4 because I had a Z4 symmetry, right? I had 4 Higgses. Screw it. Let's take Z equals 10, N equals 10, Z10. This is going to now have to be to the 10th power, K to the 20 over 16. By changing things, I mean, it's not the best to add in things, but this is appearing, this is taking the log of the problem, right? Which is what we sort of define by success. By taking n up to 10, you can really kick this thing down as small as I want, which is fine because this term might exactly be this dotted dashed line I drew, right? Okay, so great. Any other questions? So far, this is all at tree level, which is unfortunately going to be an issue. Okay, so the claim is at tree level, we have gotten a solution to the hierarchy problem. Just set the Higgs mass as small as we want. Perfect. we have a successful implementation of the idea. May not be the most beautiful one because I think you need z of this to 10 if you really want to put M Planck here and everything. But okay, I think actually it's 8 to get to 100 GeV, but whatever. Okay, so what is, you'll notice, one very important assumption here, which is that it's actually that I wrote polynomials here, right? I did an EFT here. And I guess, I don't know how much you guys have studied about EFTs, but you can do a Taylor expansion only if nothing goes through 0, right? So in other words, these are polynomial functions of everything only as long as no mass is equal to 0. Well, shit. Stuff is going through 0. And why is this a problem? Let's just say I relax my assumption of writing polynomials, right? I relax this assumption. Fine. I'm going to write something, let's say kappa squared, kappa dagger squared, v log kappa. Okay, let's go back to 4 just so I don't have to. 8 cos e to the I phi over f plus hc over M Planck to the 4th. Log of all that. The reason why I'm getting small numbers is because every time I try to write a mass term, I get k squared or k to the 8th and things like that. What's true about a log? This is log k to the 8th over M Planck to the 4th plus log cosine 4 phi over f to the 4th plus hc. I have stripped away the small number of something that's not suppressed. So, okay, logs are bad. Can I avoid logs? No. This is what happens at one loop, right? One loop. What's the one loop Coleman-Weinberg potential? V Coleman-Weinberg mh squared plus mh to the 4th times numbers plus mh to the 4th log mh squared. So, like I said, polynomials we don't fear polynomials, but logs we do. All hell breaks loose when you include one loop contributions. So, let's see, I'm not gonna particularly bore people with details, especially since I'm basically at my time. The statement is then I get terms in my effective potential from my Coleman-Weinberg. I get, that is beta functions, let's say the quartic coupling. If I repeat all this at one loop, I get a beta functions because the logs only appear due to RG running. We're talking about the Higgs mass and the Higgs potential, so we're taking about beta functions of the Higgs potential, let's say the quartic coupling. Everything goes to 0 if kappa goes to 0. So if you actually just go through the math, it turns out to be kappa squared magnitude squared, 16 pi squared. And then you get your log cosine 4 phi over f. So that thing up there, those dotted lines, well, the standard model says that it's non-zero and there's a bound on it. You can in fact just calculate what is its size. I cannot send it as small as I want. At one loop, there is something here. And so you can calculate how close do we get, right? It's this plus mh to the 4th over lambda of phi over f. So if I am Let's say I'm sitting right here. I am balancing this dotted term against this mh to the fourth over the quartic coupling. So I'm balancing those two against each other. V prime equals 0 gives beta lambda kappa to the fourth. Let's see. Can I actually do derivatives? Who knows? Derivative of this is plus mh to the squared, kappa squared over lambda f. Right, because mh squared is m squared plus kappa squared cosine phi over f. Okay. Balance this against each other. We see that mh squared is of order kappa squared lambda beta function 16 pi squared over 16 pi squared. So kappa squared is of order m so that you can turn it negative. And so this is sort of the natural value that you expect. I win by this amount, which turns out to be a factor of 100 or so because the quartic coupling is small in the standard model. The beta functions are small in the standard model. This is something like 10 to the minus 2. So you win a bit, but at least with this particular model, you don't win everything like you are hoping. If you were still at tree level, you'd be jumping up and down with joy. I've solved the entire problem. Great. You go to one loop, and you'll be like, okay, fine. I maybe put it out of range of the LHC, but I still haven't sort of done as wonderful as I would have liked. Okay, I'm basically out of time. I guess I'll go over problems and trying to resolve them later on, but any questions on the basic idea and implementation so far? All right. If not, then I guess that's it for today.